Hello, geometry. Welcome to lesson 8.2 on trigonometric ratios. This is going to be your first ever introduction to trigonometry. Trigonometry is a huge part of future math, right? If you're going to take pre-calc, if you're going to take calc, things in college, right? Trigonometry is used. Even in physics, if you're going the science route, right? So again, it's a big day here, right? This is one of those monumental steps in a math class, doing your addition, subtraction, counting to 100, multiplication tables, fractions, factoring, right, and trigonometry, right? Bunch of monumental steps, and here's one of them. So I'm happy to be your teacher for it. Okay, so let's talk about trigonometric ratios. So the idea behind these trig ratios, and again, I don't ever say the word trigonometric, trig ratios, is that you are relating side lengths of a right triangle to its acute angles. Side lengths of a right triangle to the acute angles. So notice we don't talk about the right angle, we talk about the acute angles. So in this picture it would be A and B. So here are the defined, again I didn't do this, this was defined before me, defined 3 trig ratios that we'll use. So first off is called the sine. Now we're going to use angle A to create these expressions, equations. Again, we could do the same thing for B, and I think we'll do that on another page to kind of compare, A and B, the acute angles in a right triangle. So the sine of angle A is defined as the leg opposite. So if this is A, right here, the leg opposite of A is the one that it opens up to. So that'd be BC. So BC over the hypotenuse. And of course, in a right triangle, the hypotenuse is always the hypotenuse. It's the longest side. So remember, this is the longest side, AB, right? Now, there's a shorthand method, right, to write this out. So the sine of angle A would be, and again, we think of it as opposite over hypotenuse. Okay. We also, and I'll do this too, sometimes we also, or most of the time, we also label the opposite side as the lowercase letter from the angle. So if this is angle A, its opposite side is lowercase a, and then the hypotenuse would be lowercase c, just like in Pythagorean theorem, right? So this could also be A over C, lowercase a over lowercase c. Again, my c's, I need to open them up a little bit. A over C, lowercase. Okay, cosine of A. So cosine is defined as the length of the adjacent side. So the adjacent side helps make the angle. So angle A is made up of the adjacent leg and the hypotenuse. So if you can think about that the adjacent help makes the angle, then that would be helpful. So that would be AC. It would also be side B, right? Because it's opposite of the angle B. So it would also be lowercase b over the hypotenuse, and that does not change, so that's C. And again, as a way to try to remember it, cosine of A, or cosine is equal to 2 adjacent ADJ over hypotenuse. And then last but not least is your tangent, and I'll slide this over just a smidge. So for your tangent, now you don't involve the hypotenuse. So tangent is the opposite leg. So from here, opposite would be this BC over the adjacent, which would be here AC. So BC over AC, which would be A, the side opposite of angle A, over B, the side adjacent to angle A. And again, as the shorthand, it would be the tangent of A equals the opposite over the adjacent. And again, I did not make these up. I just teach them and use them. But this is how we're going to relate the acute angles in a right triangle to their corresponding two sets of sides. There is another way, a mnemonic to try to help you. It's called SOHCAHTOA. So I'll write it right here, SOHCAHTOA. So somebody says it kind of just rolls off the tongue, SOHCAHTOA. Sure. But notice that the first letters in each of these acronyms stands for the important letters or important words used in these trig ratios. So SO stands for sine, opposite hypotenuse. CA stands for cosine, adjacent hypotenuse. And TOA stands for tangent, opposite adjacent. So again, I would not be a good math teacher if I did not show you this mnemonic. If you think it's helpful, great. Yeah, and you'll see I use it throughout the day as well. Okay, So now let's take a look at a couple questions here about figuring out what really this trig stuff is all about. So how are the sines of two different angles with the same measure related? So here's the idea here, right? We have these two triangles, right? We have x, they're two right triangles. X is in both triangles. So this x is congruent to this x. And we want to know how are the sines of these two angles B and E related. So SOHCAHTOA, SOHCAHTOA. We're going to use so for sine. So we need to label the opposite and the adjacent in each picture. Okay? So this would be the opposite side from angle x, and this right here would be the hypotenuse. So in this first triangle, the sine of B, right, which has a measure of angle x, would be equal to AC over AB. In this triangle here, from this E, DF is the opposite side, and then DE is the hypotenuse. So then the sine of E would be DF over DE. Okay, so that's good and grand, right? That's just me using, but how are these related, right? Because again, B and E are the same angle, right? Well, now let's go back to section, lesson 7.3, similarity, right? Because both of these triangles have a right angle, and because they both have x in them, these two triangles are similar. So triangle ABC will be similar, ABC will be similar to triangle DEF. So I want to set up the proportion involving these opposite and adjacent sides using my similarity statement. And again, this is by angle-angle similarity. Sorry. So AB is my hypotenuse. AC is my opposite side. So I know that AC over, and it's similar to D, or it's proportional with DF corresponding, equals, and I come back here, AB is my hypotenuse, and the hypotenuse in the other triangle is DE. Right? So here is my proportion. Now notice, how does this compare to this? Well, it's kind of similar, except, AC is on top, but AB should be down here. Well, the idea behind proportions is that you can really write them in multiple ways as long as your cross products are the same, right? If we were to try to multiply this out, we would actually multiply AB with DF, so it actually doesn't matter where the AB or DF is. So we can actually swap these, and it doesn't change the proportion, I swear to you. So if I swap them, now I have AC over AB equals DF. I'm swapping it. Equals DF over DE. Right? I swapped those two. Again, same things are being multiplied, but now I just have them together per triangle. So if you notice that this is the first one, and this is the second one. So we can substitute. We can take the sine of B and put it in place of that, and we can take the sine of E and put it in place of that. And what this shows is that if two angles are in separate right triangles, but they're the same angle, that their sine values will end up being the same. They're equal. They're equal. And this is the idea behind similarity and being proportional. Because those side lengths are proportional, these angles will have the same sine value no matter what triangle they're in. Because whatever the opposite is, the hypotenuse will be in that same proportion based off that sine ratio. Okay, so again, this is powerful stuff, right? It's very applicable to things. All right, so hopefully that helped maybe set in where this stuff comes from, I hope. Okay, so let's do a problem involving applying. Here we go. What are the sine, cosine, and tangent ratios for angle H? So this is angle H right here, right? So that's going to be the opposite side. That's going to be the hypotenuse, right? So we know that 12 is going to be the opposite. We know 15 is the longest, it's the hypotenuse. So then 9, which helps make H, right? 9 helps make H, must be the adjacent, right? So I quickly label my three sides, and now we're using SOHCAHTOA, sine, cosine, tangent, to create these. We're also going to do some division as well to get decimal answers too, because when you use your calculator, and we'll do this later on, when you type in the sine of an angle, you get a decimal number. You get the ratio as a decimal. That's just how it's stored in your calculator. All right, so let's take a look at sine of h. Well, the sine of h is the opposite over the hypotenuse, 12 over 15. Now, in some cases, I want you to simplify this. So both can be divided by 3. So if you divide 12 by 3, we get 4. Divide 15 by 3, we get 5. And then in some instances, they'll want you to divide. And 4 divided by 5 is a nice 0.8. Okay. Cosine of h. So the cosine of h is the adjacent, which is 9, over the hypotenuse, which is 15. Again, divide by 3, that is 3 over 5. And if you divide 3 by 5, you get 0.6, a nice decimal. And then the tangent of h is going to be the opposite, 12, over the adjacent, 9. Divide by 3, that's 4/3. When you divide 4/3, you don't get a nice number. So you'll see it'll ask you to round to 4 decimals. So we'll do that. 1.333. It will actually keep going 3, but we'll stop at 3. And there we go. Here's your sine, cosine, and tangent values for h. Okay, so just taking baby steps towards our real goal. And our real goal would be, if we have missing sides, can we find them? And in this case, can we find the missing angle measures of h and f? All right, so video 2 is coming up where we get more into those problems.